Okay, this is Mr. Walters. We're back. We're talking about buffers. We're talking about the Henderson-Hasselbalch equation. Talking about a lot of stuff. Lots of stuff, lots of stuff. Buffers, buffers, buffers. Blood buffers are essential for your very existence. We've talked about this before. Here is carbonic acid. There's the Ka of carbonic acid. Notice there's the Ka of the conjugate base of carbonic acid. So we have successive ionizations here. So notice we ionize, here's our acid, here's our conjugate base, and here's our conjugate base. We have another ionization there. Notice the Ka is significantly different for this second ionization compared to the first ionization. Let's see here. This is an amphoteric anion. So notice, this can gain a proton or lose a proton. It's amphoteric. The good question would be, which one is it? If you put it in water, who's going to win the battle? The basic side of the amphoterism or the acidic side of the amphoterism? Well, one thing you can do, you can take the salt form of this, which we did, which is baking soda. It's sodium bicarbonate. Take that, put it in water. It ionizes, of course, and look for a pH change. The pH is going to rise from whatever, from about 7.5 to maybe 9. So this is, it's amphoteric, but in water, it's going to be slightly basic. But isn't there another way to figure that out? Do we have to go into the lab and do we have to do an actual pH test? No, we don't need to do that. What we can do is just compare the Ka of that anion to the Kb of that anion. Notice, here's the Ka for this ionization here. So the Ka is 4.8 times 10 to the negative 11th. Notice, as we know, Ka in red times Kb in blue always is going to equal a constant value. That's the Kw value, and it's going to be 1 times 10 to the negative 14th. Just by looking at this, you can solve for Kb if you want, but just by looking at this, don't we see that Kb has to be much larger than that value? It has to be. And if Kb is greater than Ka, which it is, in fact, it's much greater, so we'll go like this, then we know that in water, this is going to act like a base in water. Of course, if we have that in water and then we add an acid to it, it's going to act like a base. It's going to grab onto that H positive, and it's going to produce carbonic acid again. So that's important. I don't know that we got that far before our break, but that's important. Just simply compare these values and you know what's going to happen when you add it to water. Well, more on buffers. There's carbonic acid. Famous chemical reaction. You're familiar with it, but it bears repeating. The carbonic acid and bicarbonate anion buffer is the most important of several different blood buffers that we have. So where does this blood buffer come from? Notice we've got huge amounts of carbon dioxide that are released from the tissue. So there's huge amounts of CO2 gas. There's plenty of water in the blood plasma. So plasma is approximately 55% water. So we got lots of liquid water. This, by the way, is an acidic oxide. It's a non-metal oxide. Non-metal oxides are acidic. So the book went through this. We didn't touch on it for this chapter because we've discussed this in kind of detail. So sulfur dioxide, sulfur trioxide, carbon dioxide, tetraphosphorus decaoxide. Put those in water. They are all acidic oxides. On the other hand, if you're more towards like copper oxide, more towards the middle of the chart, then those are amphoteric oxides. Or if you go to the far left, sodium oxide, potassium oxide, lithium, superoxide, those are basic oxides. All right, so just a little bit of review there. Anyway, here's our carbon dioxide, here's our water. Notice what's going to happen. Those will chemically react to produce carbonic acid. And with something that I didn't mention, there's an enzyme that's actually part of red blood cells. It's carbonic anhydrase. That enzyme lowers the energy of activation lowers the energy of activation and makes it much easier for these two to get to product. So in the blood we have significant amounts of carbonic acid circulating, as well as significant amounts of bicarbonate ion. So the blood buffer then would be the carbonic acid and bicarbonate ion. And there we go, there's our buffered solution here, so to speak. Of course, creating a buffered solution might be important in biological situations. If you're culturing bacteria, the bacteria may start producing acidic metabolic waste products, could be lactic acid, that sort of thing. You don't want those little microbes to ruin your experiment by poisoning each other, so you may have to create a buffered solution. A buffered solution is going to resist changes in pH. Just like this and this resist changes in pH. I've said it before and I'll say it again. Our metabolic system, the enzymes that are responsible for cellular respiration, protein synthesis, etc., they cannot tolerate big changes in acidity or basicness. What do we mean by that? They can't tolerate a 1 pH change. 7.2 going down to 6.2. Those enzymes are going to denature. They'll lose their 3D structure. That means they're going to lose their function, obviously. And metabolic processes essential for life are going to cease. That, my friends, is a problem. So buffers. I've mentioned it before in class. pH of tap water in this room's approaching 8, and they add a buffer, a weak buffer to help protect pipes. Anyway, just a little review there, important stuff. We're at that time of year where we go through new stuff and we review. And you kind of have to remember what we've done in the past, keep it in your mind, practice that, keep it in your head, and then we move forward, learn, check and correct, learn from mistakes, etc., etc., etc. Okay, anyway, so that's just review there, and I will clean this up a little bit, and let's take a look here. Let's say that we want to create a